All right. Good afternoon, everyone.
They can hear us on Zoom.
Okay. My name is Jenny Dissen. I work for the Noaa Cooperative Institute. I'm part of the Noaa Open Data Dissemination Program. I'm pleased to co-lead this particular session with Annie Burgess, who is not near me. Unfortunately, she sends her regrets. She's not feeling well. So you'll have to deal with me facilitating the session. This particular session is titled Cloud Pathfinders Assemble, and that is with purpose and intention. So I look forward to introducing our speakers and what the session is about, and look forward to an interactive discussion afterwards. There's some housekeeping things I'm supposed to cover with you, so let's just do that first. For those of you that are joining the session virtually, welcome. Unless you make a comment in the Zoom chat, which I am not checking, but my colleague here, Jake, is, please let us know that you can hear and see things, and if not, please leave us a comment on the Zoom chat. Welcome to all of those attending remotely. Okay. There are community participation guideline reminders. So by participating in the session, you agree to adhere to the ESIP community participation guidelines. Please look for those guidelines in the Word document that Jake has put in the Zoom chat. All right, so what is this session and what are we going to talk about today? Annie, who is the lead lab director for ESIP, and I have been working together for the past many months on a concept called the Noaa Cloud Pathfinders project. It involves a couple of different partners, including Noaa, AWS, Noaa Open Data Dissemination Program, as well as Noaa PIs and scientists that have been working to conduct their particular research effort in the cloud. We started down this particular program for a number of reasons. So Noaa, as part of its program, NOD, you will hear me constantly say NOD, Noaa Open Data Dissemination, puts Noaa data in the cloud with 3 cloud partners. You've probably can find or have heard more about this, but as part of our program, we make data available via the cloud partners, and making data accessible without information and understanding about use and access and discoverability continues to be a challenge. Within Noaa, our scientists also are limited in their ability to have access to a sandbox environment to conduct some of their research. So one of the big questions and challenges that we faced with the research community that we're faced with was related to having an opportunity to conduct and pilot and have access to a sandbox environment. So we brought this to our partners, our cloud partners, as one of the key areas of interest. How can cloud partners learn about scientific needs for tools and computing, and what are some of the challenges that scientists face? And it turns out that we were able to kind of create and launch this Noaa Cloud Pathfinders project. We, as part of this inaugural effort, kickstarted an effort with ESIP, largely with Annie Burgess, who is our primary partner. AWS provided cloud credits in a sandbox environment, and ESIP helped manage, facilitate, and help launch this, working with the NOD team, the Noaa Open Data Dissemination team. So in effect, that is sort of the background. We submitted a solicitation across all of Noaa for Noaa scientists to express interest in participating in this pathfinding effort. And the intent was here, quite simple, how would you like to conduct your current research in the cloud with the sandbox environment? So today's session is really going to share the experience that our pathfinding experts have experienced over the last 9 months. It has been a very interesting, productive, and challenging journey for our PIs. We have started with a variety of different levels of experience with cloud and cloud computing, and particularly cloud tools. So you will hear a variety of that perspective come through. We have these lightning sessions for about 7 minutes by our Cloud Pathfinder project PIs from Noaa. some who will be joining remotely, some who are here in person, and some who have submitted videos. So I look forward to a variety of different presentation modes and the challenges that come with it. So Jake from ESIP is going to help get us started. Our very first introduction is actually to the Noaa Open Data Dissemination Program itself. So our program manager, Patrick Cowan, who's joining virtually, is going to kind of provide a very brief overview of what is NOD, why is it important, and how is NOD working with ESIP and our cloud partners, including AWS. I'd like to personally acknowledge Chris Stoner from AWS, who's here in the room. I think a lot of what we have discovered over the last 9 months in climate science computing in the cloud is because of the access to the sandbox environment and the Noaa and the AWS solution architects that have been supporting our team. So thank you to Chris and her folks. Okay, with that, I would like to pull up our first presentation by Patrick Cowan, who is participating virtually. Patrick, if you would like to unmute and say hello.
Hello, everyone, and hello, Jake. If it would be easier, I could share my screen. I'm not sure if that'll work for you.
Okay.
Yep, that would be great. Let me make you co-host. Okay, you should be able to share.
Patrick, can you share the slides from your end?
Yes, they should be coming up. Do you see that now?
Yes, we do. Thank you.
Okay. Well, I'll take it away. Thank you, Jenny, and thank you, Jake, and everyone at ESIP for allowing me to be here this afternoon, even though virtually. I would have loved to be in Pittsburgh, but that is okay. I will get over that by the end of the day. So good afternoon. My name is Patrick Cowan. I'm the program manager of the Noaa Open Data Dissemination Program, or as we refer to it, as Jenny mentioned, NOD. The other NOD team members are Adrian Simonson, who is our director, and John O'Neill, who is our technical advisor. Then we also had the folks from our data broker team at Csps, Otis Brown, Jonathan Brannick, Jenny Disson, and Dennis Willett. And just a quick programming note for those who may be unaware, may be wondering, NOD versus other things they heard. We were formerly the Big Data Program, or the BDP, and I'll touch on the evolution of becoming NOD in my third slide. So today I'm just going to give a quick overview of NOD, a little bit of the background, mechanics of moving data, metrics highlights, and an introduction to the reason why we're here, which Jenny already did a little bit of, the Noaa Cloud Pathfinders program. I'll try to keep this as brief as possible. So first, I just wanted to quickly touch on the reason why NOD came to be. So overall, Noaa as an agency was concerned about the increasing volume of data collected, stored, and archived, as well as the increasing public demand for the data that we collect. So Noaa was also focused on reducing stress on its on-premise dissemination systems and improving services for users. In addition, it was beneficial that the idea of NOD supported the Evidence Act and the federal data strategy requirements for open data. And lastly, making Noaa data easier to use democratizes the data and enables innovation. So this slide gives a quick look at the timing of BDP's evolution into NOD. So the Big Data Project research phase began in April of 2015 with the signing of 3 non-competitive cooperative research and development agreements, or CRADAs, with Amazon Web Services, Google Cloud Platform, IBM, Microsoft Azure, and the Open Commons Consortium. In 2008, the CRADA was extended a single year. And then in late 2019, previous statement, that was 2018. In late 2019, the Big Data Program operational phase began via no-cost, indefinite delivery, indefinite quantity, or IDIQ contract with Noaa selected partners, AWS, Google, and Microsoft. And then with the passage of the FY22 Omnibus Appropriations Bill, the Big Data Program became Noaa Open Data Dissemination, or NOD, as we refer to it now. So next, I just wanted to briefly give an overview of the NOD contracts. So Noaa signed contracts with the 3 cloud service providers I mentioned previously for $250 a piece. These contracts represent partnerships based on mutually provided value. The contracts provided needed certainty for both users and Noaa that data will continue to be provided through this program. Each contract requires the CSPs to host a minimum of 5 petabytes of Noaa's data with no costs for the storage or public egress of those data. The contract also allows any Noaa line office that signs a separate storage and compute contract with one of those 3 CSPs to avail themselves of free public egress for that data through the Open Data Dissemination Program. And also note that NOD inside of Noaa is an enterprise public data dissemination option available to all the line offices and data providers within Noaa. It is not intended to replace any of the major dissemination mechanisms throughout Noaa that many folks here may be familiar with and are often required by mission goals. So next, I just wanted to quickly review how NOD delivers data out to the CSPs. So on the left side of the slide here, there are pictures representing the data that Noaa collects and some of the observing platforms used to collect that data. All resulting data, as you can see by the dotted line, being within our federal security boundary on the left. If you follow the arrow over to the right, you'll find the Noaa Cooperative Institute of Satellite Earth System Studies, or Csps, which is NOD's trusted data broker. So Csps is allowed inside Noaa's security boundary to retrieve data sets, which it then transmits to the CSPs, which in turn provide the data to an exponential number of users, enabling their innovative data analysis and decision making. I want to note that it's becoming more and more common for Noaa data owners and programs to push data out to NOD, eliminating the need for the data broker to go in and retrieve those data sets from internal Noaa systems. Again, increasing the security of those systems. The data broker monitors data flows from source to destination, resolves operational problems, and supports the development of metrics, and helps to develop and implement approaches to ensure end-to-end data integrity across that pipeline. The data broker certifies the CSP holdings as authoritative Noaa data, and in many cases backfills near real-time cloud holdings with complete period of record for data sets from Noaa archives. And here is just a quick overview. I'm not going to touch on everything on the slide, but one of the most essential parts of NOD is the data broker function that I've mentioned. Csps provides flexibility, agility, and innovation in developing R&D technical processes for data delivery. This is critical since each data set is different, as is each line office and each CSP. NOD adapts to each unique situation. However, the goal is to significantly reduce the data broker involvement over time as Noaa itself becomes more adept within the cloud. In addition, Csps manages the resource and access controls for NOD's holdings on the CSPs. So for instance, they create and generate buckets and containers, and then provide those credentials and information out to data owners so that they can move data into those resources. Given that the data buckets are outside of Noaa FISMA boundary, a third party like Csps is critical to owning those data buckets instead of Noaa. There are many other activities listed here the data broker is involved in. I just, within my 5 minutes today, I will not spend time discussing those. So one of the other critical elements that the data broker provides is leading our engagement efforts that are listed on this slide. For the sake of time, I will not discuss all of these either, but here are many of those for your awareness. I did want to, however, note that the Noaa Cloud Pathfinders program that was mentioned earlier that we're here to discuss today was initiated in conjunction with AWS by Jenny Disson, our user engagement lead. All of this engagement gives us the ability to learn data sets of highest interest, concerns about latency, and questions about format conversion. Through this interaction, we understand the user and their use case for the data. So my next slide here, I just wanted to quickly highlight one of our most recent kind of wins, and that is a prototype metric reporting tool for NOD data sets, which will provide NOAA leadership and relevant program and data owners metric information similar to what you see on the screen here. Note that the use of NOD does not require users to register on or be authenticated on any cloud service provider to access the data, and the rules governing the cloud service providers severely limit their use of user identifiable information. Obviously, that makes it a little bit harder to develop metrics, but the data broker has found ways to take access logs and similar things and generate this type of information. So NOD continues to work with each of the CSPs to gain access to this information and use and access the data in the storage counts. Understand the data they can make available via metrics, and also continue to develop user understanding based on engagement, interactions, and communications. All of this to assess NOD and its data's overall value to NOAA and the user community. So for the sake of time, I will not go into these numbers, but one kind of highlight on the page on the left at the top, you can see there's over 22 petabytes of total storage being utilized for NOD right now across all 3 cloud service providers. So this just brings me to my last slide. I will not spend much time on this because Jenny did a nice introduction, but I also do want to specifically thank Chris Stoner, the Open Environmental Data Lead on the AWS Open Data team, for her support and guidance on this project. It definitely would not have been possible without her support. So with that, I'll turn it back over to Jenny and Jake to start the discussion on the 5 NOAA Cloud Pathfinder projects that are happening across NOAA and ECIP and AWS.
All right, thank you, Patrick. That was a great overview of all the NOAA data that is available in the cloud across our 3 cloud partners. So let's just get right into it. As part of our NCPP cloud pathfinding projects, we have 4 of those presentations being shared here today. So this time I'd like to invite Steve Olsen and Shane Mills, who are both part of NOAA National Weather Service. I will have them share their particular experience and journey, but I would like to say, as we transition to pulling their slides up, there's a before and after. What was their state of the knowledge and working in the cloud before they started down the path, and where we ended up? So feel free to have a discussion around that and have a full appreciation for the journey. Okay, so Steve and Shane, both of you are online virtually. Thank you for your time and attendance. Take it away, please.
Okay, Jenny, just real quick, can everyone hear me okay?
Yes, we can.
Okay, very good. Okay, so our particular cohort study was involving exploring cloud backends for the new Open Geospatial Consortium Environmental Data Retrieval API. Next slide. So I'm going to start with a little bit of a background. Oops. Let's see. Yep. The agenda, we're going to talk a little bit about a background, some purpose and approaches, some key findings and takeaways, our testing methodology, and then get into a little bit of a demo, next steps, and why this program was so important. Next slide. All right, so a little bit of a background regarding our study. The environmental data retrieval is an OGC RESTful API standard, making it easy for users and clients to access a wide range of data, gridded observational data through what are called uniform, well-defined, simple web browser interfaces. Basically, the EDR provides just the data that a user is requesting, hiding the underlying complexities of the storage technologies. So graphically, if you look at the graphic there, EDR is this abstraction layer between all these disparate systems and formats. EDR homogenizes that data, and to a user, they see all these structured and standardized URLs that allow them to do feature extractions from sample coverages. And that's done through a variety of sampling geometries, a position, an area, or a polygon, radius, cube, trajectory, corridor, location, and items. Next slide. All right, so the purpose, early prototyping efforts for EDR began in 2020. And the focus for those was on the integration and homogenization of all these different disparate systems, whether it's threads or local FTP service or what have you, different sources and formats, ways that we could automate the process for the homogenization of that data, and then of course the discovery, dissemination, and actual visualization as well. And we're going to demonstrate that for you here. A number of line offices became very much interested over the past year in the prototypes that we were doing based on our implementation of EDR, both as a dissemination mechanism as well as a visualization mechanism for their applications. And so the purpose of our study was to explore and assess what an operational implementation of EDR would look like, particularly for the cloud. And the intent is to essentially move away from a server environment to a scalable serverless environment, one that allows for a lot of horizontal and vertical scaling to handle performance, particularly in heavy use. Next slide. All right, so with this, I'm going to turn it over to Shane to talk about the approach that was used and some of our findings.
Hi, everyone. I'm Shane Mill from the National Weather Service. So yeah, like Steve said, we had started with basically a server environment, and we were looking to move towards a serverless environment. So the tooling used, we really were looking at AWS CloudFront, API Gateway, Lambda, and we really wanted a centralized DAS cluster to do the backend processing of the Noaa data. Next slide. So here's the overall architectural design. Like I mentioned, CloudFront, API Gateway were the big ones, getting into Lambda. And then you see the centralized DAS cluster using Fargate. And then the reach back to the two S3 buckets, one which was a nod bucket for the National WarML. Next slide. So the summary and key findings and takeaways. So in this implementation, we had never dealt with a serverless environment before. So with we found very quickly that CloudFormation was a great way to have these templates that configure and automate the deployment of these different AWS resources that make the front end and back end services of the EDR API. On the front end with CloudFront, CloudFront is huge for caching, but you have to manage costs. So we found that setting a time to live header on the object saved cost versus constant validations of the objects. And then we found an immediate performance boost with CloudFront and a cache hit. For example, a data query for a month worth of hourly data for the National WarML gave us 11.28 seconds without CloudFront and then 53 milliseconds for the return with CloudFront. So that's a huge improvement. Next slide. And then API Gateway was very easy to implement the EDR API spec because API Gateway can ingest an open API definition. The CloudFormation, like I mentioned, helped automate the deployment of this environment. We really then focused on the DAS cluster and having a DAS cluster that the different Lambda functions could reach to on demand. So we originally looked at parallel cluster, but found that ECS with Fargate was much easier to implement, especially with the connection between Lambda and that centralized cluster. Next slide. So now that we have this implementation, let's get into the results. So we're testing the original server environment and then a serverless environment in US East 2 and US West 2. We have a couple of different EDR API collections of data. We're testing different spatial coverage, vertical and temporal ranges, and different load ranging from 10 to 500 concurrent users. Next slide. And then now we'll get into the test results. So next slide, and we'll go pretty quickly through these results. All right, so here we have the serverless East with 10 concurrent users. Notice the distribution is basically most requests are responded to within 2 seconds. Next slide. And then as we get to 50 concurrent users, we see a very similar distribution. Next slide. And then with CloudFront, you see pretty much most of the responses backed up right to under 500 milliseconds. That's because most of these are now cache hits, which really improve performance. Next slide. So the same type of distribution for West, slightly different response times, but a similar distribution with the serverless environment. Next slide. Similar distribution with 50 concurrent users, and then next slide. And then with CloudFront, again, we're getting much better performance in the serverless environment. Next slide. All right, so now here's the server environment, and the server environment's already being overwhelmed with 10 concurrent users. And we put things in place to try to have some horizontal scaling using gUnicorn, and there's a local DAS cluster, but you still see much worse performance. Most of the responses between 5 and 10 seconds. And this is only with 10 concurrent users. Next slide. Even worse performance with 50 concurrent users, most responses over 25 seconds. Next slide. And then now we're drilling right into a specific query. So this is a GFS query for one time in the full realm of Z values. This is with 50 concurrent users, and we see a similar distribution to what we've been seeing with the serverless environment. Next slide. Same with West, very similar distribution. The next slide. And then server already is really having a hard time with 50 concurrent users. Next slide. Now we're bumping up to 100 concurrent users. The serverless environment's still doing a pretty good job. There's no failed request, and we're generally in an acceptable term for response times. Next slide. Same type of distribution for the West deployment. Next slide. And then server, again, is just now at this point a total mess. No responses are coming in past like 10 seconds. So pretty poor performance. Next slide. Now we bump it up to 500 concurrent users. We're seeing some degradation in performance, and that could be related to the DAS cluster. And we can configure that to improve this performance. And we're seeing failed requests now about a quarter of the time. Next slide. Very similar for West. Next slide. And then server East doesn't fail, but no request really succeeds. Like we're looking at a minute to like 5 minutes in these responses. So horrible performance there. Next slide. So I pretty much went over the key findings. So next slide. All right, so now we'll get into a demo. Let's see what the serverless environment looks like in action. So next slide. So here we have the national water model. It's basically 1 month of data that's being requested, and it's hourly data, so it's quite a bit of data. To the left, we have the DAS cluster, which is running on Fargate. Basically, the request is returning coverage JSON, which you can visualize within a UI with that line graph. If you were to click on the NCPP Serverless East National Water Model 1 month at the bottom, so the link to the right, go ahead and click that. Yep. So this is the caching with CloudFront. You get an immediate response right away. If you were, and you don't need to, but if you were to click the other link, it would take about 6 to 10 seconds. So that's just demonstrating the true improvement with the caching too. Go ahead to the next slide. All right, now, so you have this OGC EDR API hooked up to a Noaa data set. Like what's the use here? You're really accessing the data with structured URLs, but a big goal of the OGC APIs is interoperability through building blocks. So if we put the EDR API with the OGC API processes, now we have the UMV components of the wind coming from the EDR API, but then you're playing a process API on top of that to calculate the wind speed and wind direction. And you're seeing the visualization of that here within this client. Next slide. Now, here's another example of the OGC API process and EDR API integration. This is a client that shows the process API, and we've built out many computational classes here. This is an example of the thresholds. So basically here, a user supplies a threshold, the process API calculates that threshold based on the EDR API data that comes from the Noaa bucket. So the contouring you see here is in GeoJSON. So a user could download many different output formats, but the GeoJSON will basically give you the geospatial area that meets that exact threshold. So the big perk to this, you're giving the user directly what they need. They don't need to post-process the data, but also for the provider, they're disseminating much less data. So that's a big perk to these interactions here. Next slide. So go ahead, Steve. Steve, you may be on mute.
I am on mute. Thank you. So to expand on this, so we have now been able to implement what I would consider to be a baseline serverless environment. The next things that we want to look at are the refinement of the memory allocations for our Lambda functions, investigate compression for what gets disseminated out to users, investigate an asynchronous approach for requests of data that cannot be handled through Lambda, but through another means. We want to refine the CPU and memory allocations for Dask, and then investigate as we move forward here pub/sub mechanisms to support the subscription service to data. Next slide. Just want to close on just why this program was just so important. So three big points for me. The first is that this program provided an opportunity to speak to, leverage, and learn from AWS experts on how specific applications might assist in our conversion from a server to a serverless environment and its evaluation. It just goes without saying that that just completely jump-started and sped up the amount of time it would have normally taken to do that, and it's just so invaluable. The next thing is that the ability to discuss the other cohort studies and the types of applications that they are looking at in their studies may not have been initial focus of our effort, but that's not to say that downstream we couldn't learn from their study and apply some of the technologies that they have applied. So just the ability for the awareness and the ability to reach out to them post NCPP is also very invaluable. And lastly, and this can't go understated enough, with cost always being a factor, we probably wouldn't been able to do such an extensive testing without the access to those free assets. The ability to learn, and we did learn a lot, greatly enhanced our ability to look at cloud technologies for the OGC EDR API. And then lastly, next slide. With an eye towards cloud technologies and obviously where you could link APIs to data as a whole, whether that's NOD data or other data, having something like an EDR is very, very important. It allows for us to obviously do a lot of scaling, vertical and horizontal scaling to increase demands. And certainly, you saw one particular piece here of the environment. So the ability for a user to directly interface with the NOD data, both from a dissemination standpoint, from a process standpoint, from a visualization standpoint, and the dissemination of that back out is, I think, something that will become more and more crucial going forward. And I believe that is it.
Thank you, Steve and Shane. What a journey. So I imagine there's some questions, and I think the room here would like to applause. Okay, so we do have one question here which we can take briefly, and please know that we have a good 30 minutes at the end of all the presentations with all their journeys to talk about each of the experiences themselves, but we'll take one quick question. We have one in here in the room. Yes.
Possible naive question here. I noticed that your architecture was heavily dependent on caching strategies, but you were talking about a query API, and I'm wondering how much you can leverage caching given possibly the variation in queries and also the changing data that those queries are responding to.
Steve, do you
Shane,
want
you
me
want
to
to take that first?
Yeah, sure. So yeah, that's a great question. It's a very dynamic API, and we're coming across that use case quite a bit. A lot of the time you could basically set up tiling for different regions, and then that tiling will definitely lend better to caching for that geospatial area. When you give the user free flexibility over selecting different polygons and things like that that they're within control of. You could set caching to hit their queries as well, but you're right. Like unless you have predetermined areas and bounding boxes, it is difficult to capture every type of behavior for caching.
Thank you. Okay. Please keep those questions coming if you don't mind to reserve those towards the end, but we will take one burgeoning question that you can't wait. I invite our next speaker, also from Noaa and CEI, to share their particular experience. This is with Crowdsourced Bathymetry project. And so John Cartwright, who is joining us virtually, if you can unmute and please tell us about your project.
Okay, would you like me to share my screen or do you want to try to increment through my slides?
Yeah, I think it seems like it would be easier if you would like to transition the slides from your end. So if you give me 1 second, we will make you a co-host. Okay, it is all yours. Take it away.
Okay, let me share my screen here. Just 1 second, please. Okay,
John, all looks
Jenny,
good
can you?
here.
Okay, great. Well, great. Thanks for that, and I'm excited to be able to talk to you about building a bathymetry data access and management system in the cloud. And I'm doing this on behalf of myself and my two collaborators here, Jennifer Jinks and Georgia Zelenik, who are not here today, but greatly helped in this work. So first of all, let's take a look at why. So what is bathymetry and why does it matter? Bathymetry, or the mapping of the seafloor, is critical, obviously, for navigation, but also for modeling of things such as ocean circulation, benthic habitat distribution, weather systems, tsunami wave propagation, and of course, climate change as well. This importance is recognized in global and international initiatives such as Seabed 2030 and the US NOMAC. Yet despite all of this, only about 23% of the ocean floor has been mapped by direct observation. And it's clear that traditional surveys conducted by governments and academic institutions are just not going to be able to close this gap. So this is where crowdsourced bathymetry comes in. The International Hydrographic Organization has partnered with Noaa to promote and standardize the voluntary collection of bathymetric soundings recorded just on standard navigational equipment that these commercial and private vessels use while they're engaged in their routine operations. These data are then submitted to the Data Center for Digital Bathymetry, which is hosted at NCI in Boulder, where the data are ingested, processed, and permanently archived. So why the cloud then? The crowdsourced bathymetry data has the potential to produce huge amounts of data with potentially exponential growth. And this is not well suited to traditional relational database management systems. So hosting the data in the cloud offers both scalability and data storage as well as processing capability. A system like this, you've got very bursty sorts of requirements. So you may get a lot of access and it may sit quiet for minutes or hours or something like that. So that scalability is really important. There's also the potential for significant savings in the software development and maintenance by using managed services. That's things that you don't have to maintain your own infrastructure, and that can be a big win over traditional on-premise solutions. The operational cost benefit from the serverless pay-as-you-use, again, kind of referring back to that bursty nature of the use of these systems. And the commercial cloud providers offer a lot of flexibility with literally dozens of managed services to choose from, and the ability to quickly spin up resources to prototype various approaches. Finally, building a cloud-hosted system to access the CSB, the crowdsourced bathymetry data, has the potential to be a pathfinder for other completely unrelated projects, but which have similar data requirements. And also, the CSB data files were already loaded into an AWS S3 bucket as part of the nod that we've heard about. So the data were there. So although the data were there in the nod and accessible, they're currently there as a collection of files organized by date. And this is less than ideal for the end users, as it leaves them with the responsibility of aggregating, subsetting, and reformatting the data to meet their specific needs. With this in mind, a couple of years ago, NCI undertook a pilot project to provide seamless access to the CSP point data and offer on-demand gridding of the extracted points. All of this exposed via an HTTP API and a simple asynchronous ordering system. And this first phase was generally successful, but it was limited to CSP data. So the second phase that we undertook through the help of the NCPP was to expand this, rebuild it, and integrate multi-beam bathymetry along with the crowdsourced data to support additional attribute constraints in addition to just geometry, and to increase the data automation and data management tools. So this involved almost a complete redesign, and I'm not going to dwell too much on the architecture of the first phase, but it essentially had an API gateway, some lambdas behind those endpoints. We're using DynamoDB for managing the state information that's shared between the various components. Amazon Athena, that we'll talk a little bit more about, and an EC2 instance, which is actually using the MB system open source software to do the gridding. So the request comes in, it's extract the points, you do the gridding, you dump the results in an S3 bucket, and you email the user, and they can come pick it up. You'll notice that we're using the data directly out of the nod as part of this. So, oops, I seem to jump too fast. We used a number of AWS technologies or services, but I want to focus in on just a couple of them that I thought were particularly interesting and particularly important to this project. The first of these is Athena and Glue, and it's a little hard to tell. Athena and Glue work very closely together, and it's a little hard for me to tell exactly where one ends and the other begins. So Athena is really about doing SQL queries on structured data collections. So in this case, we had all the crowdsourced bathymetry data sitting there in a S3 hosted or S3 bucket, and we were able to build this virtual table on top of that data, and then issue just kind of standard SQL queries. I've got a little example there in the corner of the slide, but basically just standard SQL. And in this case, we were taking a bounding box and pulling out the data that fell within that bounding box. It's important to note that Athena is doing asynchronous queries. So it worked very well for us in terms of these batch kind of operations. But if you were trying to hook up a web front end where you were expecting to get kind of real-time responses, it doesn't work quite as well for that. One other thing that we spent quite a bit of time on was, because Athena charges per query, or for each query is charged based on the number of data, on the amount of data scanned, and this is a public-facing API, we had to be careful about the cost. And so we spent some time looking at various data optimization strategies, things like eliminating unnecessary attributes or converting date strings to binary date date types, and using the Parquet format, a column optimized storage format, and even doing some spatial partitioning using Uber's H3 tiling scheme. So various strategies to try to reduce the amount of data that are scanned and therefore reduce the operational cost for each query. There's the Glue is the managed ETL service that works very closely with us, and it essentially provides these table constructs that Athena operates on. So, data can land directly in the S3 bucket in its CSV format, and it's automatically available to the S3. In our case, we were converting those data to a Parquet format to optimize the cost, but even that can be automated. As the data lands, it can trigger a function that processes those into a Parquet format. The second service I'd like to call out is the step functions, which we're using to orchestrate the processing flow. This is essentially a state machine. And in our first project, our first pilot, what we did is we wired everything together. We had a bunch of lambdas and we're using a bunch of messaging. And that worked, but it as this got more complicated, as we brought in the multibeam data and the processing got more complicated, it was harder to track. And so the step functions were just a beautiful approach for us to be able to orchestrate all the processing and have it very visible. You can see on the right side, this is actually what the console looks like for the step function. You've got this visual environment that you can wire together tasks. You have access to any of the AWS services, but as you're running this, you can see the data flow through the task, and you can even inspect each task and see the data, the message that's coming in and how it was mutated and what comes out. And so this became a very powerful way to tie together as the processing got more complex. You can handle error conditions, you can handle asynchronous tasks. I was really impressed and pleased with what we were able to do using these step functions. So just to kind of close out here, I'd really like to call out the role of the NCPP and providing a sandbox for prototyping, a flexible environment that we could try things out and burn them down quickly when they didn't work, but also having cohorts that were doing completely different projects, but it was a valuable forum for sharing ideas and kind of learning what other people were doing and just being able to exchange. And finally, being able to talk to the AWS subject matter experts. For example, as I'm digging into ways to do this spatial partitioning and some of the behavior I was seeing with the Parquet formats in the CSV data, it was really great to be able to engage those folks at AWS and kind of talk through some things that would be more difficult through more traditional channels. So I know that was a whirlwind through, but I'm going to wrap there and I'll turn it back over to you, Jenny.
Right. Thank you, John. That was great. I particularly enjoyed the slide with the icons of Amazon tools that you can use. So for those that are listening, there will be a quiz. I hope you can name that icon. Okay, one quick question, else we can move on and save our discussion to the end. Hearing none, we now will move on to our next presenter. Also a Noaa Cooperative Institute Fellow. You may know of him already, Doug Rao. He has done a number of sessions and presentations here already. How he had time for this is just amazing. Doug and Jessica Matthews, who is a Noaa NCEI scientist, worked on climate data records, and he will tell you more, but he's here in person, so ask him all the hard questions.
Right. So thanks, Jenny. And so we are one of the 5 projects that actually, it's more on the research and user engagement side. We're mostly focusing on the how we can use it.
Those watching virtually, we are in the process of sharing Doug's presentation. Give us a second and he will start over.
All right,
Okay.
thanks.
All right. Thanks, Doug. Will you start again, please?
Right, thanks, Jenny. And again, we are one of the 5 projects that's more on the research and user engagement side, where we are thinking about how we can really let people to use the data that's already put on the cloud. So one thing we are specifically focused on is the Noaa's climate data records, which has been in an operational program since 2010, or started 2010. I couldn't remember what's the exact timeline, but both Jessica and I use a lot of climate data records or CDR data lots. And since it moved into clouds, and it has been quiet, I haven't seen anyone directly using any data on the cloud. So that leads us to think, so a traditional pipeline is that the researcher producers put the data into a server or data archive, and then the data users with experience and knowledge, they will start using those data. But oops, I don't know why it advanced, but Oftentimes when users from different sectors try to use the data, they will ask, where's the data and how to access and what does the data mean and how they can use those data. That often requires, if it's the traditional way, you need to download this data and to open the data files, looking at the documentation, looking at data file structure, and to use it. And all the CDR data are stored in NetCDF, which means you need to know how to use NetCDF files. Not all the people know how to use it. I still remember when I was doing my PhD, my former colleagues who are ecologists, asked me how I can open a NetCDF file and to use the air temperature data that provided by Hadley Center from UK. So he has been in ecology field for more than 20 years, and so that it's a really valuable data set for them, but they just don't know how to use it. So for the CDR, for people who don't know about it, I will not talk a lot about details of the technical things we use, because it's really simple. We basically use S3, EC2, and Fargate. That's the only three things we use on AWS to do this. And for the CDR, which is long-term satellite-based, mostly satellite-based data to generate those long-term time series for climate monitoring and research. There are 4 different categories: fundamental CDR, atmospheric CDR, oceanic CDR, and terrestrial CDR. So putting all of them together from Noaa NCEI website, you can find nearly 40 different CDR products, and that has been produced in operational capacity for people to use. So we want to make sure those find the whole entire workflow and pipeline from find to access to understand the use much easier to do. So the file download access sometimes can be challenging for people to really use the data sets. And then once you download this data, and then the formats can be another barrier for users to use. And how can the portable tools and services being developed to really facilitate the use? So the whole goal is trying to see how can we provide tools and services to enhance user experience of those CDR data sets. So our project, we name it Climate Observatory. So there are 3 components. So with the workshop, which is trying to convert those data set into an article that has been mentioned so many times during the Easter meeting. I don't think I need to explain what article is, but for us, we are converting the NetCDF files into ZAR for the analysis, and we experimented with different chunking to make sure, at least based on the pilot data set that we're looking at, is a NDVI, normalized difference vegetation index, which is daily frequency file at 5 kilometer resolutions for the entire global land surface. And we experimented with different chunking size to make sure the performance is optimized in a way in the several scenarios we tested. And the second piece is the dashboard, trying to develop a web-based interface where users can customize data visualization. So without really downloading the files, opening up the files, they know how this data will look like if they choose this data for their analysis. Right now, we have those pre-computed anomaly time series and anomaly maps for the entire land surface, as well as for selected regions, pre-computed for different regions based on the IPCC climate report. So they have the interactive atlas. We use the same climate regions to do that. And then the final piece of this project is the studio is trying to create notebook-based tutorials for learning, so that provide a way for users to use both the native format, NetCDF format, if they consider they want to download the file, which we discourage people to download files. So try to put them into the ZAR route to use the CDR data in the ZAR format. And the final piece I want to share is that today, actually at the teacher workshop, I was able to use some of the tutorial and notebooks, teach some of the high school teachers at the Easy Teacher Workshop to visualize some of the CDR data, as well as that for them to use it with their students. So it's only in the 30 minutes slot that I have, they were able to visualize the NetCDR, the NDVI data, and then they're excited to show those data to their students. So I think for us, the technical side is really straightforward. The community has been working on it for a while, but we're just trying to apply those technology to really increase and engage with the users to make sure those data can reach the values of that.
It's terrific. Climate data records, for those of you that would like to learn more, and the audience here would like to applause, please. Thank you, Doug. That was great. For more information on climate data records, I just encourage you to find out more about it by typing in Noaa climate data records in the search box. For those of you checking the text in the chat remotely, I put the link in there, and it's also in the document that we are following along with. I will take one pressing question. If not, we will save all of our questions and discussions towards the end. Okay. Now we have one last presentation, which is a video. And the video is by another NCPP cohort member. Her name is Maureen Taylor. Maureen worked with a couple of members from her team, Chris and let's see.
Oh, sorry. Josh and Maureen.
What was that? Oh.
Maureen.
Oh, okay, great. So Maureen is unable to join us, but she has shared with us a video of her particular experience. And, you know, being that there were 5 projects that were part of Noaa Cloud Pathfinder initiative, each of them came from a different part of Noaa, each with a different type of data and different type of project. So this is one of those projects. And what I'm pleased to share is that some of these projects are looking to continue and extend. You've heard from 4 out of the 5 projects from the Noaa side. We also have experience with another agency. We do have one more speaker after this, USGS. Rich Signal will kind of share his experience. But what I wanted to share is that there is so much interest in being able to access a sandbox environment to experiment that I think 3 of these projects are looking to extend and continue. So I just, you know, for Noaa and government scientists to have the ability to access a cloud environment is already wrought with barriers and challenges from a security perspective. So this was possible because of our collaboration and partnership with ESIP and AWS's contribution. So in that context, I wanted to celebrate and recognize that, you know, climate services further progresses and advances when we lean in and collaborate and partner. So with that, let's hear from Maureen.
My name is Maureen Taylor, and I work at Hello everyone. My name is Maureen Taylor, and I work at Noaa's Northeast Fisheries Science Center in Bristol, Massachusetts. I'd like to take this opportunity to provide an overview of our Noaa Cloud Pathfinder work and our experience over the past 6 months with this audio presentation. I'll talk a little bit about the project itself, but also we'll touch upon why we pursued the Pathfinder program, what our journey has been like along with our project outcomes. Our project is called OASIS, which stands for the Oceanography at Sea Information System. It supports the Ocean to Climate branch. Personnel Rose is the lead of their hydrographic monitoring program. Joshua Moser has been our project manager, and my role has been to develop software for data transfer from the ships out at sea to object storage in the cloud. In essence, this really has been our beloved world first exposure to using any cloud resources within our work environments. So in order to talk about our project motivation, I'm going to give a very brief overview of the Northeast Shelf Ecosystem Monitoring Program and what role the OASIS software has in it. The first track shown on the left part of the screen is the monitoring area, the land in the upper right corner is Nova Scotia, Canada, and at left is the northeast coast, U.S. coast from Maine to North Carolina. And under the sampling here, when cruises are collected, the ships don't have too many mechanical issues. There are roughly about 1,500 CPD, connectivity temperature test tasks, that are collected each year from a variety of North and Center field programs. The CT instruments are deployed off the side of the ship and get lowered to a few meters above the ocean floor, collecting vertical profiles of temperature and swimming. The one shown in the photo next to the ship has a carousel above it, which is used for ocean chemistry sampling. And smaller CT units are also routinely deployed with small nets attached to the program for practical sampling. So the original intent of OASIS was to provide our background rapid data collection to help ensure that sampling and accessing data processing methods were standardized and done correctly. And starting in about 2009, when most of the ships had barely reliable internet, we started sending the data files nightly using an SFTP transfer to a server back on shore. And in doing so, the oceanographers back in the home office can keep tabs on the data and provide feedback to an ongoing survey. And this cruise track figure is an example of just that. Chris Melrose puts these together each day using the uploaded data files. And also about 2009, the Ocean Climate Branch upon request started to make this preliminary data available to external partners outside of Noaa who wanted access to near real-time data in order to initialize their regional ocean circulation models. So we used this data flow for quite a few years, and about a little over a year ago, we received a number of broadcast emails that announced the Noaa Cloud Pathfinders program, and that's what we decided to apply. We wanted to explore a new data delivery model. This was an opportunity for hands-on learning using our existing OASIS project. There have been both training and network opportunities during the last 6 months, and it has allowed us to take the difficult but necessary very first step to evolve our applications to use cloud technology. So instead of uploading the temperature and saline data files to the server at our home office, we developed a C#.NET application using the AWS software development kit to send the preliminary data to an S3 version bucket. And there were really 3 objectives that we saw. Number 1, the Ocean Climate Branch can continue to engage with an ongoing purpose in order to optimize shipment, which is very expensive. It still allows them to ensure that the data are of the highest quality possible. And number 3, it still allows them to provide access or request to data from outside the world. We encountered a number of challenges during the last 6 months, most related to security concerns, the nature of the data that we're dealing with, and simply doing something new. These slowed us down a bit, but with each hurdle we were able to present the very benign nature of our project. These data can and are made up. We had a number of meetings with our local security officer, fisheries CIOs, to describe the project and the data. We began communicating much more about our work at local communities in practice and at our change control work to let them know what we were doing and that more projects like this would likely follow in the future. We received support and advocacy from Pathfinder sponsors, and our 6-month journey culminated in a successful pilot deployment of this last month. So these are just screenshots of our application that are shown at our Pathfinders cohort meetings. We received some excellent feedback from scientists around the test groups, and we continue to learn and hope to improve on this. So going full circle now, this cruise track on the left was made by Chris using the data in the S3 bucket from the pilot groups. The animated GIF shown at right shows the actual profile of temperature and salinity along the cruise track when you click it, so it plays. This was created by Jim Manning. Jim is an oceanographer who over the past 2 decades has done quite a bit of cooperative research with lobstermen and citizen science projects to high schools in New England area. He included this in his newsletter that he sends out to fishermen who likely often see the Noaa ship offshore, but may not always be aware of the kind of data that we get. So what comes next for us? We have another meeting with the fisheries CIO's office early in August. We will definitely share the lessons learned with others. We need to develop a local process for cloud project intake, and our Pathfinders experience will definitely support that process so that roadblocks are minimized. We're going to try running our project again in the fall, where we might have 2 shifts out at once. And lastly, I'd like to acknowledge the learning opportunity that the Pathfinders program offers us to gain experience and incorporate cloud solutions into our existing OASIS project. We learned about what the other teams were working on and what their journeys were like as well. And we were often humbled by how much further along the other projects were in their usage of cloud resources. But that also became a motivator for us as well. We got to start somewhere. Also, thanks to both the Ocean Climate and document the branches and really lining our story for all levels of the workflow journey. If you have any follow-up questions for me, I can reach the detail I share. Thank you.
I'll be glad to message Maureen about the loud applause in the room. This particular project is a personal favorite of mine for many reasons, but the institutional barrier that we experienced at Noaa to get Maureen up and going because of security issues was just incredible. And you can just think about the importance and the value of conductivity, temperature, and depth information for a fisheries center that reaches a number of different stakeholders. The positive outcome from this particular project is, they're able to now have conversations, and the OCIO out of that office is very interested. And I think in general, across all of our cohorts, there is ongoing conversation about, how do we incorporate this? How do we make public access to the data and the findings? And so hopefully this is just beginning of more projects like this. So with that, I would like to invite our last presentation, Rich Signell from USGS, to come on up. I'm glad to know that it's also in-person presentation. And while his presentation is being pulled up and shared, I'm going to pass the mic over to you, Rich, so that you can introduce yourself, please.
Yeah, Rich Signell, USGS, and I helped Annie Burgess set up this little cloud sandbox environment. So I just want to talk to you about, some of you have been using it today, but for those of you who haven't tried it out, I'm just going to talk to you about like some of its the features of this thing and what you can do on it, and actually how you could spin it up for your own organization if you wanted to. Yeah, so the goal was to make it easy for some of these folks who wanted to experiment with cloud native workflows, just as you heard about in some of these other projects. QHub is a open source project that allows you to deploy Jupyter Hub on Kubernetes with Dask Gateway, and it's actually funded by Amazon through their with Amazon credits. And what it gives you is a shared users group. You can have different groups actually, but everybody right now is just in the users group. But you could have special groups if you wanted just to do stuff off on your own and you didn't want other people to see your notebooks or something like that. There's a shared S3 bucket. There's shared folders, as I just mentioned. So you can, if you do work in the shared folder, the users can see other people's notebooks and you can help debug other people's problems, things like that. And the really kind of killer feature of QHub for deployment is that you can create environments on your own as a user for yourself or for other people in your group without any admin person intervening. So you can create a fully functioning environment that works with all your Dask workers and all the versions agree because of this cool thing called Condastore. I just wanted to point out though that QHub is one way to deploy this kind of thing. There's a lot of other ways. 2i2c is a really cool project also that has infrastructure you can deploy to do this kind of thing. And they also provide services if you just want to pay for somebody else to maintain this thing for you. And Saturn Cloud also provides a service that you can like spin up a Jupyter Hub with Dask. And then Coiled is a company that allows you to actually create Dask clusters anywhere on the fly. So is it the plus, or how do we go to the next one? Is it? Okay, so just click. Okay. So yeah, some of the cool features of QHub, as I mentioned, are obviously that it has Dask Gateway, that's the big thing, but some of the other kind of cool, and Condastore, which I just mentioned, this ability to create your own environments or for other people in your group. It also has workflow scheduling. So if you create a notebook and you're fooling around and you get something you like, you can actually submit it through like KBatch cron job, so you can you could actually schedule something to run on a, to update. Say if you were doing like a Kerchunk workflow and your model output was showing up in a bucket, there's new data showing up, you could run like a Kerchunk workflow, and it would actually use the Kubernetes cluster just to to do that work on some kind of schedule. That's just a simple example of a workflow. It also has VS Code built in. So if you don't want to just sit there in the notebook, if you love VS Code, it's available to you there. And they also have some other stuff for like monitoring what's going on with Grafana and integrated video chat. Actually, that doesn't work very well. And so, you know, you could also look at this if you wanted to. It's just a simple way to deploy Pangeo, you know, which is really just, which really just means that you're doing like stuff with cloud optimized data using, you know, things like X-ray and HoloViz and stuff like that. There's environments you can just use there that are already built if you don't want to build your own. And so a lot of people were doing that today. So actually, but you know, so it's kind of amazing that somebody like me who can like deploy and can maintain this thing. And this is because it's just a simple configuration file. Everything runs on it's Terraform, and it'll deploy on Amazon or Google Cloud or Azure or DigitalOcean. And you just edit this config file. On the left, you probably can't read it, but you do things like specifying like, you know, what size instances you want to have deployed and where you want this thing, you know, running US West 2. And then when you make changes to this thing, you know, you just go to GitHub, you click the little edit button, you know, change the configuration and you know, merge it, and it kicks off GitHub Actions that deploy everything. So if somebody says, oh geez, I need some more memory, I need 32 gigs of RAM or whatever, no problem. Just edit this file, boink, and then, you know, when they log in, there's like a new instance type. So yeah, showing over on the right, there's some GitHub Actions from that, you know, happened recently. So yeah, so, you know, it just looks like regular Jupyter Hub when you get in there. You got your Dask cluster up on the right. This is actually from earlier today. We were running the crew chunk tutorial. A bunch of people, new people signed on, and ran the crew chunk tutorial. And this is what I love this the best. This is this is Jared Peacock, who did the whole thing during the conference on his phone. He logged in and like did the git clone and like changed the notebook and then ran it all on his phone. And there's the proof, his little right there. So that's it.
All right, well, that was great. Thank you, Rich. So the floor is yours. I have questions, but I have done enough talking for today. So for those of you that are in the room, what questions do you have of all the presenters?
Hi, I'm Brian Bonlander at NCAR. We are using Jupyter Hub sort of deployed within our NCAR environment. But I'm very curious to ask this question, which is by essentially figuring out a workflow to run in the cloud, are you tied to using the cloud after this, or is this in a way a way that you've by creating these workflows, you could, let's say the cloud disappeared tomorrow, could you, I don't know, use these configurations potentially to just deploy to somewhere, maybe your own environment or something like that? Has it freed you in some sense by performing this, by going through this exercise, or are you in some ways, you have a better like environment, potential like target environment for running this that's maybe independent of any specific provider?
So I think, what is working? Okay, yeah, sorry. That's a great question. And I think like everything we do, like on the Pangeo project, but I think also most people who are working in this arena are doing things that that can work on any cloud, but can also work, not on the cloud. And you can, of course, you could, like if the commercial cloud providers went away, you could still host your own object storage if you wanted to work with object storage that way, right? And you could use compute from your HPC center using all these same tools, at least in the things that I was showing. I think things that Matt showed and other people did. Obviously you're not going to be, if you're dependent on serverless functions, then then that might be an issue. But I think most of these things, they're just using serverless function because they scale and they're quicker and, but there are ways of, I don't know, do you want?
Our virtual presenters and listeners, I just wanted to invite the opportunity for you to unmute and comment. Oh. Okay.
I don't want to speak over anyone else who wants to respond to that. I called dibs on the next question.
Yeah. I think we'll take the next question.
Thanks. I'm Leslie Shee from USGS. I love how there's a cohort and they meet weekly, and some of the presenters mentioned that they wanted to share what they learned with others, maybe outside of the cohort. So I'm just wondering, what do you think are the easiest next steps to do that? Because of course you can always talk to your friends and co-workers that you already know, but like, what can you do beyond that to spread all of the knowledge that has been gained in this cohort?
We are actively working on that very same concept, but I just want to make sure that Shane and Brian and Steve and anyone else who is virtually listening, please let us know if you cannot hear the question, and please just jump in if you would like to make a comment. So we are just wrapping up this is our first set of presentations that we have publicly shared. After this, we have a branch seminar that we will share our experience with the Noaa folks. Some of these projects, especially within the National Weather Service, is quite an opportunity within our NWS office. So we're having our own special gathering between the Noaa team and the National Weather Service team to help understand and share their journey and the experience, to help kind of create a sense of comfort and overcome any fear or barriers, or use that as an opportunity to address the technical questions that is sometimes, occurring within our own offices. We have plans to extend some of the projects into the next phase. And I think that they will scale and get a little bit more complex. And so I'm already thinking in my mind about some interns that we can bring on from other parts of the Noaa enterprise. But community sharing. So of course, presenting at AMS and AGU, and any opportunity where our cohorts are invited to present at USGS or NSF, it is for them to say yes or no. You can always ask Annie, she will. But we're happy to talk about it.
Jenny?
Yes, please, comment. I think that's Shane.
Brian. I think I put this in feedback to you. I think it for some of the projects, maybe in like weather service, and Noaa in general, we've got cloud setups that we're working on for operational use. And I think the next steps would be to transition or work to figure out how to transition what some of these prototypes learn to the operational setups that are being worked on.
Yeah, thank you, Brian. I might add that, it is non-trivial. It might sound like it's happening, but I think there's a lot of work to be done internally. But it's happening.
So I actually had a question about the Noaa Climate Data Record project, which sounded very cool. My question is, the czar stores that you're creating, are these like things that are one-off and then they're static? Or are you like getting more data in that you have to update? And if you're having to update them, how are you handling keeping that updated while potentially people are like accessing the data at the same time? Like, is that an issue you've run into, and how do you kind of deal with that?
So right now it's only...
Doug, sorry, can I ask you to repeat the question so those that were listening could hear.
Yeah, sure. Thanks. Maybe you can repeat the question on that phone because this sometimes doesn't work.
Okay, and I will do my best to recap, so please let me know. The question was really on climate data records. So as these projects are occurring and satellite data is being updated, how are we making sure that the cloud updates are reflecting, how frequent are the CDRs updated, I think is the question.
So actually, not quite. So, okay, when you, so you talked about chunking in your czar store, and I'm assuming that you're chunking like across time, like you have multiple, right? Okay, so you get in, say, a new record, and you have to update a certain number of chunks in your czar store. But potentially somebody, while you're doing that, is reading the data. So have you thought along those lines, like how you're going to deal with that? Like how do you maybe notify users or protect them from like seeing those updates? Because they might then get like sort of a strange, like half updated, half not updated state while they're reading.
Okay.
So right now, this is not, sorry, this is not the operational side, on the operational side. So it's more on the static side. We have completed all those historical CDR data in one batch, but this is something we are talking about because we have some plan to extend that to not just one CDR and also extend it to more operationally, that can serve some other parts of NOAA. For example, some of the national water model folks interested in using some of the CDR data as a comparison with their model output. So this is one thing we're going to try to use the event triggering, because that when there's new data go into the AWS S3 bucket of the CDR, specific CDR, that will notify this new CDR comes in, and then we will do the updates, do the conversion of that into a ZAR, then make them into the sorry, the ZAR format of data. But one thing, that's the unshared secret piece of CDR I haven't talked about, the not so good piece, which is that CDR currently, there's no operational mirroring between the data on the NCEI website versus the one on the cloud side. So right now we still need to cleaning up some of the old files of CDR that should not be there. So one way to say it in a not so bad way for NOAA, which is that we are in the transition process for from the into the new satellites to extend the CDR, because the CDR used to be developed based on FHRR and all those old sensors, and now with a lot of new sensors from NOAA and other agencies, we're updating the CDR, extending it by using those new sensors. But there's a transition period. There's some preliminary data from the data which should be deleted already from the NCES, which is official records on the NCES. It has been deleted, but those has not been updated on the AWS side. So that caused some confusion if users want to use those files. We're dealing with it right now. So.
Just one thing that's kind of cool about object storage, though, is there's no partial like files. Like it's either like not there or it's there.
Okay, yes, absolutely, and that is fabulous. But a lot of times what happens is that you get, well, with us, is you get in your data set as, say, all the data for a single day, just as an example, if you have daily data, okay? But then the data for that single day ends up going into multiple chunks in ZAR because of the way you've chunked it, and each chunk is a separate object. We've now killed that question.
Yeah, Alexander Leonard from HDF. I don't know if you're thinking how to update, but basically, unless your new data appears in the ZAR JSON, it doesn't exist. In other words, you can create your chunks, I don't know how many. Once you update the JSON of the ZAR array, at that point, whoever accesses it will be aware of those new chunks. So I don't think there is a problem at all. So yeah, okay. I'm giving whoever next, but I'll have a question.
Just
so, look at me again. So I think the first talk mentioned something about 10-year agreement and something about free egress cost and things like that. I wasn't quite sure in the sense free to whom. And so that would be maybe interesting to clarify.
Yeah, I'm part of the program, the Noaa Open Data Dissemination Program. I can answer that question.
Please.
But what is the question?
Yeah, so the question was, someone mentioned there is a 10-year agreement, and as part of this agreement between Noaa and the cloud providers, the egress cost of the Noaa data is free. So my question was, before, or if I was to download those files or access in any way outside of the cloud, was that the requester pays or not? And so that means free to me or free to Noaa?
Okay. So Noaa data today is available from the Noaa NCEI website and any other Noaa line office. You can find that information. It is available via FTP sites. Other universities and other partners also offer Noaa data for free. When we started the Noaa Big Data program, which began as a research effort with our university partner that I'm part of. As part of the research effort, the idea was, can we develop the pipes and wires to go have access from within the Noaa FISMA boundary and make that data available via the cloud partners? It did involve partnerships, contract vehicles, agreements with our cloud partners, understanding of, what and how we would go about this, that kind of thing. So when we set up the agreements, we piloted a number of different data sets that were made available for free via the cloud. So there's no before. There was no data available via the cloud, arguably. At least no environmental data. That's not entirely true, but in the official sense. So does that answer your question? So you can still currently access Noaa data off the cloud from the Noaa NCEI websites and other Noaa sources.
Jenny?
Oh. Well, yeah, I was gonna let,
Yes.
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 Gonna let AWS answer that. Thanks, Chris.
So I can only speak on behalf of AWS, but when data sets are added to the Open Data Program, we cover both the monthly storage costs, so you don't pay a monthly storage bill, and we also cover the egress costs. So that means Noaa does not pay a monthly storage cost, and Noaa does not pay an egress cost. Yep.
Yes. Yep. Harder question is why, but. Somebody on mute? No, he's not there. Okay, so our session is slated to end at 5:30. We are past time, which is a great sign that this was a great session. I'd like to once again thank our speakers and those attending the session. Thank you for being here. I am happy to continue the discussion and dialogue. I sense that there's some burgeoning questions that people are just feeling a little shy to ask, so I'll stick around. But otherwise, I think I'd like to thank you, and I'd like to thank Jake and Isip for pulling this off.